Well, sometimes we need to switch the order of integration, as we've seen in some other examples. Now, there's no real need to switch the order of integration in this one, but I just wanted to use this as an example. So rewrite the integral with a new order of integration, dz dx dy. Right now it's dz dy dx. So we have to look at the region. Z is going from 0 to 10 minus x minus y. That would be the plane, z equals 10 minus x minus y, and z equals 0 would be the xy plane. Y goes from 0 to the square root of 16 minus x squared. Well, if y equals the square root of 16 minus x squared, I think it's obvious that we have a circle of radius 4, but since y starts at 0, then it's only going to be the upper part of that circle. So we got a semicircle, and x goes from 0 to 4, so we're starting at the yz plane and going out to 4. So here's that region described in the picture. The rainbow color is the plane, z equals 10 minus x minus y, and above the xy plane, that's where this little red quarter circle is. It would have been a semicircle, and from here to here it was a semicircle, but then x only goes from 0 to 4, so we chopped off that part of it. So this hue, the pinkish above the red, below the rainbow, and inside this quarter circle. So now how do we switch the limits of integration so that it goes dx and then dy? And so this is pretty easy. The z limits are going to stay the same. X and y needs to be adjusted a little bit, but if you say, well, that circle would be x equals square root of 16 minus y squared, that would put us in the right half of the semicircle, or right half of the circle, and then y goes from 0 to 4 would put us in the same place. So this integral should give us the exact same volume as this one. I didn't compute them, so I don't know if my software will even do this. Let me see, what does it say? There we have a number, and I hope we would have the same number for this one. With our limits switched. If we don't, then I'm back to the drawing board, huh? There it is. Oh, isn't that nice to see?